Okay, this is just a short little bit at the beginning here because I wanted to show something again, and it's likely to be in the first video. So, dot numbered positions, delta x, and then our delta t, the t average, the center of the bin, and then we have the v average, delta x over delta t, and then I graphed them, and it's got a negative slope, which is not what we want. So we need to remember that we started, if we call the bottom of the ramp 0, and the positive directions down the ramp, that means any position going up the ramp is a negative number. So we say equals -1 times, there it is. Now this thing has got some weird formatting, this table 2 column 5. I don't know how to get rid of that. And then I just go down the line, and then I copy this and I put it here, and and I paste it, but now it's no longer, what I don't like about this, it's no longer a formula. So I realize what I can just do. I can just take this and go -1 times, and I think that's what I actually did in the first video. Okay. Alright, so I'm going to pause this and I'll get back when I'm happier with what's going on. Oh yeah, and then notice the graph. It's just what we want. Okay. Pause. Okay, so now we're back. So I've gone through the 2 sets of data for up and down. I see that I haven't added error bars to this one, but you can see for the down here, the error bars are quite small. Oops. And so let's go ahead and let's see. I don't even know if there's any error bars at all. No. Now, it would be neat if I could just add just the 1, but I guess not. Okay. So chart design, trend line, no trend lines. Let's call it standard error. Now I have both X and Y, and of course we're assuming there's no error in T. It's kind of difficult to, when you do chi-squared fit, to deal with those anyway. So we just want to make fixed value at 0. This is in the first video, and for some reason, what did I do wrong here? Oh, I got it. X error bar, oh, fit. So does that add error bars to both of them? Oh, goodness gracious, yeah, so you have to do that. So I thought when I did these up here, it didn't add it to both. Oh boy, okay. So that stinks. 0. Then, of course, this is for the fit line, so they both have to be 0. Okay. And then the now there's the data points, 0, and then now finally we get to something meaningful, and the Y error bars are custom, and then we go over here and we see del plus minus V average. Unfortunately this ink is on it, but oh, I could just start selecting from down here. There we go. And same thing. It's kind of boring because they're both the same and they're not very large. And there you see them. They're a little hard to see, so what I can do is I can do the series, and then I can do marker option, and I can make them smaller, the dots. So we can now sort of see the error bars. They're still not easy to see. Okay. So in this case, I'm just wondering why there's a dot. A data point up there. There shouldn't be. Because that's just an extension of the fit line. And the X values are okay. And the Y values are, oh. Okay, I see. I've got to pause this a moment. So I got that text out of the way. Let's see, select data and edit the V average. Okay, that's fine. I see the X values are a little off. There we go. And now the Y values. There we go. The whole data set got shifted a little bit. And there's still a data point there. Okay. Select data. Fit. Edit. Fit. Nice. Then the X values. Now I added these two to extend the line. And then, yeah, there we go. Good. And so say okay. And so we're just going to have to understand what's going on here. Series fit. Interesting. I thought. Interesting. So why? Solid line, marker. Let's go built in. None. Okay. It still seems to be the average. Okay, so I'm going to pause this. There's something wrong with this graph I want to fix. It's bugging me. Alright, so now I got all that. I just don't understand why this one is got. Let's do this. We'll make the error bar 1. Oops, no, wrong thing. Yeah, plus or minus. Let's make it 5. There we go. But it's still 3.29, and that is weird. So that means that there's some kind of misalignment here. So I think I know. So this blank space is involved. So I'm going to get rid of it. And then here, yeah. Then, oops, wrong one. And I'm just get rid of that. I think that's, yep, there we go. Now the error bar looks right. Okay, so I'll just put it back to what it was. I don't remember the formula right now, but they're very tiny. Now they're all consistent. And of course now I have to add the fit line, which is getting tedious, But now you see I've added these two extras, and that just allows the fit line to extend. I think I've put it in there, but in the previous video. And now I say okay, and then I'm going to format the fit line, and that's the paint can. And I'm going to say solid line. I'll make it thin. And then marker option, none. And there we go. Beautiful fit line. Great. Okay, so let's go through it. So I've already done everything. So, so first of all, let's go through the justification. And where did that go? And so I just made one mistake here. Excuse me. So this is plus, and this is minus. So let's make believe that the track is tilted a little too much. So it makes the acceleration larger down the track. So then when we measure A up, it's going to be larger than if we measure A down. And so that's why we're putting plus there, because it keeps the sign consistent. Because if we find out that it's actually tilted the wrong way, then we're going to get a negative value, and then we plug in a negative value here, and you're subtracting it, because then if it wasn't tilted enough, then the acceleration up is going to look a little less, and the acceleration down is going to look a little bit more. Because, give me a minute, let's make sure I'm saying this right. So if there's an extra tilt up, then, this is funny, I keep thinking I have this straight. I mean, it works out, but hold on, I'm pausing. All right, look at that. This is why you repeat these things over and over, because I just realized that I made a mistake. Okay, so we define ALE as the leveling error. And then A of F is the friction. And it's the change in it's the element, the part of the acceleration that comes from friction. So A of up measured is going to equal to the acceleration of gravity. Acceleration of gravity. And we're going to say that if the leveling error is positive, so it's tilted more than we think, then that's plus the leveling error. And friction is always pointed in the opposite direction of travel and the velocity vector. So the initial velocity vector, well, the one that we care about, it's up the track. So the friction will point down the track, the opposite direction. Then for A down measured, it's going to equal the acceleration of gravity once again, plus A of the leveling error. And now, since it's going down the track, the acceleration error caused by friction is going to point up the track, minus. This is different than what I said in class. Don't sweat it. So now, if I take the average, so that means I add them together. A up measured plus A down measured divided by 2. And you see that the frictional elements cancel, and you're left with the acceleration of gravity plus the acceleration due to the leveling error. So the difference between them is then, well, let's do the difference. So they both would have some leveling error that'll affect them both the same way. So then when we get the average, we will remove the effect of friction. And then if we take the difference and divide by 2, that's going to equal now. So the AG's cancel, the LAD. So this is going to equal to the acceleration due to friction. And let's see now. So that says then the we'd expect that number to be small. In this case, what's going on is that this data I got was taken by a professor of all things, and it's still not good. I had a monkey with it, and to get numbers that approximated. So you'll see, excuse me, here that see delta t is 0.09, and here it's something similar, 1/7.45. Pretty stupid, but I needed to make these things look good. Okay, so anyways, we'll cut this and put it back as a picture so it's easy to move around. So let's think about this. And So then that means so we eliminate the leveling error. We eliminate friction when we take the average. And so let's see this. What I have here now is A up is larger. Yeah, that makes sense because friction would be pointing down. And then A down is smaller because it's pointed up. So, okay, so that's consistent. And we noticed that the friction is 5.6. So these guys are meaningless now. So I'm gonna just get rid of them. And let's see what I get here. And we'll bring these guys closer. Copy. No, I want to cut it, not copy it. Cut. And paste. Of course. All right. So the difference between accepted and measured is equal to absolute of accepted minus measured, which is the average, and divided by the average of the two numbers. AVERAGE, average of measured, comma, accepted. Oops. There it is. Entered, and that's not so bad. Oh, wait a minute, we're not supposed to do that. We're just supposed to do the difference for now. That's right. Just the difference between them. 2.75. And then the percent difference equals this divided by the average of this, comma, accepted, enter, close, and then times 100. All right, so we have a 0.28 percent difference, and we still have to I don't have the correct plus minus up here. Okay, good. So all we have to do is finish that. And I want borders. There we go. So this is, and these are all in centimeters squared per second squared. Copy. And paste. And then, yeah, they're all in centimeters per second squared, aren't they? Oh, not percent difference. And that one doesn't go. All right. So we need to get the percent of the error bar on this. So I go to data and solver, And so we want to get the value, make it the value of, what is it? Some of the 154. It's odd that it's different. The bottom one is 700 something. Okay. So sum of the chi-squared is 155.26. And I only want to, and it's this chi-square, sum of, and then all I want to do is vary the slope. And then I say solve. And, well, I say okay. Then I copy this, paste the number. So we end up with 0, of course. And now go to the solver. I want to minimize that, and just to make sure that I'm not fooling myself, I'm going to use both parameters. I'm going to solve, and yeah, look at that, the sum of the chi-square is the same. So we have a 0.25% fractional error, and the difference is 0.28. So that's pretty good. I basically say that we've declared victory here. Nice. And then the difference told us that, so that's interesting. I wondered if there was a way to get rid of the leveling error. And I might yet have made a mistake here, but yeah, because friction is going to affect things the opposite direction, but the leveling error is going to affect it. Oh yeah, so that means that at the moment, we could say that the error, the difference, we got it pretty darn level if we only have a 0.28%. So the difference, in principle, is only caused by the leveling error. Yeah, okay. And, oh yeah, just to be certain, we take the, here, I forgot this part, let's just, here we go. So, we remember in lab we said A is G sine of theta, which happens to be little h over h, right? Opposite over hypotenuse. So we don't even need to know what theta is, so it's just G h, little h over capital H. And then if we want to know what is the acceleration of gravity measured, we just invert this and bring it to the other side. And if you look carefully, that's what's here. See, these two boxes are highlighted. And I just happen to put dollar signs on it so I could move it other places. Okay. And then, of course, now let's see now. Then it means that it says plus or minus this. And yeah, so I just, all I had to do was scale the plus minus. That was easy. When it comes to averaging, you, right, you average the two plus minuses, but then we add them, And divide by the square root of 2. What if we take the average and divide by the square root of 2? Is that the same thing? Because you don't divide. So let's see. Let's see. We have 1.26. Yeah, the average has got it. Yeah, it should get better than 2.46, but let's just be safe. Okay, so we'll say here equals this plus this, and divide by SQRT 2. Yeah, right. So I had it right the first time. You average it and then divide by the square root of 2. Okay. And then, oh yeah, so we need to get that has 0.25%, and this has 0.11%. So actually, we need the fractional error on the G measured. Let's see how we're going to do that. On the average, what's a convenient place to do it? Yeah. Let's insert row. There we go. And then we're going to say frac error in percent. And that equals to this divided by that times 100, 0.13%, and then the difference, the percentage difference again between the two numbers is 0.28, so the error bar is smaller than the difference. Okay, 0.13, so it's half. So now what I would say is then, yeah, the difference is the leveling error right now. And so it's interesting. And this is just a note to myself. This gives me the friction and the acceleration of friction if I take the difference and divide by 2. So the difference between accepted and measured is 2.7, and that's at 2.28% apart. But our error on the actual measurement, so we believe that we measured very precisely the acceleration of gravity, and so this says that the difference is caused by the leveling error and not by our technique. It would tend to say we'd have to do other experiments. Cool. Okay. Time to publish this bad boy.